Hello everyone, and welcome to my channel. This channel is for educational purposes, and we try to look at theories of everything and cosmologies, all-encompassing theories, people who work their whole life on something and put it out and never really got any credit for it, other important scholarly work or research work that has been suppressed, and anything else that might really benefit your life if you knew about it, which you probably don't. And today is our 408th video that we've done on the reciprocal system of theory. And this system of theory was proposed originally by Dewey B. Larson when he came out with his two fundamental postulates in 1959. Then he took those two postulates and through a process of deduction deduced his theoretical universe. So he boiled down his two postulates to really two sentences and then took those two sentences and said, well, if this is true, then that's true. And if this is true, then this follows from that. And so if my postulates are true, this is what my universe would look like. And then in his books over the next 30 years, he compared his theoretical universe with the empirical universe of the legacy science. What they, over the course of the centuries and millennia, through thousands, if not hundreds of thousands of scientists and billions, if not trillions of dollars worth of research work and grant money and so on, what they had finally compiled in their scientific tables and so on from their laboratories, what the what the universe looked like. And we're looking at one of the results of that, his book, Larson's book, that's called Basic Properties of Matter. We are going through chapter 1. We started this 3 days ago, so if you want to go all the way back to the start of the book, you go back about 3 days. We're still in chapter 1. Which is called Solid Cohesion. So in this book, Basic Properties of Matter, Larson focuses on chemistry, and he focuses on his theoretical universe in terms of some of the basic properties of the elements of the atomic table and the chemical compounds. So he looks at things such as solid cohesion, the interatomic distance, the compressibility, and the melting point and the critical point. These different measurements that legacy science made in the laboratory, Larson comes up with values for these things strictly from theory, and then he compares the results. So we're going to go through that in just a minute. First, I just want to give you a quick once-over on what are the fundamental postulates and what is Larson's worldview about this. Larson's universe is also known as universe of motion because Larson says that the universe is not made out of matter. It's not made out of energy or force or something like that. Energy, the universe is made out of motion. And in Larson's estimation, which is kind of what distinguishes him from some of his predecessors who also had the idea that the universe was made out of motion, is that he defines motion as the relationship between space and time. It sets up a generalized reciprocal relationship between space and time. So space and time are the components or the contents of the universe. Motion is the contents of the universe, not the setting. In thousands of years of science, all of the basic paradigm is that the actions of the universe take place in this setting of space and time. But in Larson's universe, space and time are the contents of the universe. And motion is basically a fraction, with space or time as the numerator and time or space as the denominator. Example, speed. The bicycle is moving 12 miles per hour. 12 miles of space in 1 hour of time. Space over time. Speed is space over time. And you can see the reciprocal relationship if you decide to double the speed. You double the speed, now you can say this the bike is moving 24 miles per hour. Or you can say the bike is now moving 12 miles per half hour. You can multiply the space or divide the time. That's a reciprocal relationship. So as far as speed goes, at least we can see that there is a reciprocal relationship between space and time as far as speed goes. But Larson applies this to all of our real scientific quantities, not just speed, but energy, matter, force, acceleration, pressure, electric charge and electric current, magnetic flux, surface tension, power, density. These are all relationships between space and time. So that does represent an improvement over the MKS system, which requires really space, time, and mass. And it becomes complicated when you got 3 variables there. Larson boiled it down to 2, space and time. Now, when Larson talks about motion, he talks about a more generalized, non-localized kind of motion that he calls scalar motion, which is a motion that has a magnitude, but it has no specific direction. It's kind of like a more abstract version of motion that you can envision using a balloon, spotted balloon. And if you blow up the balloon, all of the dots will be moving away from each other. Each dot is moving away from each other dot. There is no specific direction that they're moving, just outward. They're moving outward away from each other, but in no specific direction. And likewise, if you suck in Larson refers to this as the progression. If you suck in the balloon, and now the balloon is contracting, all of the dots will be moving toward each other. And this is the opposite force there, or not really a force. He'll be talking about that today, but it looks like a force because a force is an action at a distance, and it is seen to have a direction. This inward force, this inward, what Larson calls as-if force, like so it looks like a force, but it isn't, is what Larson refers to as gravitation. All of the dots are moving toward each other, but they're not moving in any specific direction. But if you arbitrarily decide to assign one of those dots as being the reference point and say that it is motionless, then you can start kind of seeing force fields between the dots. Like this dot is moving toward, all of the dots will be moving toward this motionless dot. And so you can see that it appears to be a force, but it isn't. The force is the direction is the result of the reference point, not a result of the motion itself. The motion itself is just a motion of all dots toward all other dots. And so that is also part of the reciprocal system. And then another major part is the discrete unit postulate. Time and space and motion come only in discrete units. You have to have a full unit of space and a full unit of time before you have those entities. And if you have exactly 1 unit of space in 1 unit of time, you have what Larson calls unit speed, otherwise known as the speed of light. So the speed of light in Larson's system is 1. 1 over 1 equals 1. And that, as you know about reciprocals, is the center. So whereas legacy science takes 0 motion as the center, Larson's universe of motion presumes a motion outward at the speed of light in all directions as the 0 point, or the neutral point of the universe, meaning that half the universe is actually moving faster than the speed of light, which Larson refers to as the cosmic sector, and half moving slower than the speed of light, which is the material sector. They are divided by the unit speed boundary. And really there are 2 other boundaries in the universe as well, a unit space boundary and a unit time boundary. The unit space boundary is within the material sector, and the unit time boundary is within the cosmic sector. If you don't have a full unit of space, then you don't have space. And so if you don't have space, you only have time, because the universe is composed of space and time only in motion. And so Larson refers to these as the time region and the space region, respectively. And within each one of those units, you have, within the space region, you have the interactions that take place within a unit of space. If they are within a unit of space, they occur only in time. And so this is the realm of the atom and the chemical compounds, molecules, small areas, less than 1 unit of space, which is 4.56 times 10 to the minus 8 meters. And when you cross the unit speed boundary, just like when you cross the unit speed boundary, you reverse the rules, reverse the order of space and time, reverse the directions of space and time. Then the other part about the reciprocal system is the three-dimensionality. Larson observed three-dimensionality of space, x, y, z coordinates in a still frame here in the material sector. And he extrapolated the same for time, because reciprocals are identical to each other. They have the same qualities, but just in a different order. And so he presumed that there is a three-dimensionality to time as well. He calls this coordinate space and coordinate time. In the material sector, you have coordinate space, and then you have clock time. The clock is always getting later and later and later and later, but in no specific direction, like a scalar motion. But when you cross the unit speed boundary, you move into the realm of the cosmic sector, and you have relationships based on coordinate time, 3 dimensions of time, and clock space. Space is always getting farther and farther and farther apart, just like on an expanding balloon. So a scalar motion. Okay, now let me just quote you the postulate, just so the universe is composed entirely of one component, motion existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is not as important, and I think we'll just leave it off here for today, but it is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Okay, now we're going to get into this discussion on the solid cohesion. Solid cohesion is something from the time region. So it is an atomic phenomenon. It has to do with the progression, because within the time region, the progression moves everything toward each other. And gravitation moves everything apart from each other, because you have to reverse the directions when you cross that boundary. And so there is an equilibrium that is established between the two as you know, 2 atoms approach each other, you know, within a unit of space. They find an equilibrium distance that balances out the progression and gravitation. The progression which moves them inward, the gravitation that moves them outward. And Larson calls that the interatomic distance. And if there is a force that moves, that aids gravitation and moves them further apart, there is a force of cohesion that resists that force. Or what Larson calls an as-if force. So that's what he's looking at in this chapter. He just kind of went through a lot of the history of science on this and was talking about how the basic, the scientists, the legacy sciences theory on this is the electronic theory of matter, where, you know, matter holds together because of chemical bonding and electronic forces, you know, positive and negative attraction. And Larson says that that doesn't cut it, because it only applies to a small amount of compounds. Most of them are non-ionic, and even if they were, you would have to have 2 different forces, not just one, to establish an equilibrium. There would have to be a force of attraction and a force of repulsion, which is built right into his system, and which also he applies to many other things in the universe, not just this one. So, you know, he characterizes the legacy sciences approach as ad hoc, because they're just kind of making up stuff for one specific pigeonholed, you know, area of their science, whereas Larson is using a generalized theory, and the progression and gravitation fit in perfectly in this theory, but they also fit in perfectly in many other applications. Okay, so we'll start it right here. As indicated in the original discussion of gravitation, even though the various aggregates of matter do not actually exert gravitational forces on each other, the observable results of their gravitational motions are identical with those that would be produced if such forces did exist. The same is true of the results of the progression of the natural reference system. There is a considerable element of convenience in expressing these results in terms of force on an as-if basis. And this practice has already been followed to some extent in the previous volume. That was his earlier volume called Nothing But Motion, which is on atomic physics mostly. Now that we are ready to begin a quantitative evaluation of the interatomic relations, however, it is desirable to make it clear that the force concept is being used only for convenience. Although the quantitative discussion that follows, like the earlier qualitative discussion, will be carried on in terms of forces, what we will actually be dealing with are the inward and outward motions of each individual atom. While the items that have been mentioned add up to a very impressive case in favor of the new theory of cohesion, the strongest confirmation of its validity comes from its ability to locate the point of equilibrium. That is, to give us specific values of the interatomic distances. As will be demonstrated in Chapter 2, we are already able, by means of the newly established relations, to calculate the possible values of the interatomic distance for most of the simpler substances, and there do not appear to be any serious obstacles in the way of extending the calculation to more complex substances whenever the necessary time and effort can be applied to the task. And it would probably help Larson if you'd had a computer or even a calculator to do most of the work. But he was using a slide rule most of the time. Furthermore, this ability to determine the location of the point of equilibrium is not limited to the simple situation where only the two basic forces are involved. Chapters 4 and 5 will show that the same general principles can also be applied in an evaluation of the changes in the equilibrium distance that result from the application of heat or pressure to the solid aggregate. Although, as stated in Volume 1, the true magnitude of a unit of space is the same everywhere, the effective magnitude of a spatial unit in the time region is reduced by the interregional ratio. I did do an episode on his paper on the interregional ratio. It seems to be kind of ad hoc, but he uses it in every application that he needs to use it. It is convenient to regard this reduced value, a fraction 1 over 156.44. Really, that's 9 over 1408 of the natural unit as the time region unit of space. Okay, it is convenient to regard this reduced value 156.44 of the natural unit as the time region unit of space. The effective portion of a time region phenomenon may extend into one or more additional units, in which case the measured distance will exceed the time region unit, or the original single unit may not be fully effective, in which case the measured distance will be less than the time region unit. So anytime, basically the interatomic distance is what gets lost in the translation. So when you're peering across into a unit boundary, when you're peering across a unit boundary into another region, like into the time region, what you see is not what you get. Well, maybe that's not phrased right. What you see is not what's really there. You're only seeing a fraction of what is really there because there's something lost in the translation. It's kind of like looking at the sun. If you look at the sun, you only see the surface of the sun. You don't see what's inside. You don't see the interior of the sun. You just see a fraction of the body, like what's on the surface. And it's kind of like that. I don't know if that's a great analogy or what, but so every time that you look into the time region, you have to take what you see and divide it by 156.44. That's the number that and he derived it in the episode that I did on the paper that he did. Basically, it's 128, 2 to the 7th power times 11 over 9. And hard to explain, how he got that number without further understanding of the reciprocal system. The reciprocal system is very difficult, like I said, for Larson to teach, because there's so much kind of background that you have to understand that is unfamiliar, because you're indoctrinated into a different system. And so everything sounds, it's very clunky. I think that's why it hasn't ever gotten off the ground. Not because it doesn't work and not because it's not effective, but because it's too hard to explain, because there's so much background, and it all makes sense when you finally do get it, but it's difficult to get there. That's why I would like to be working on a textbook for the reciprocal system where everything is laid out for you on a silver platter, just like little boxes on the side to explain the interregional ratio and give you all the sources that you need for that, and a little area here to explain the as-if force, of gravitation and the progression, and what is scalar motion, and what is the time region, and what is the space region. How do you determine the unit distance and the unit time, and so on and so forth. I think there is a way to teach the reciprocal system, but it's definitely a difficult undertaking. Just here, I've read 2 pages of this book, and how many different cul-de-sacs did it go down that you have to kind of explain where this came from. So Larson definitely had his work cut out for him, not only in deriving the theory, but then explaining it is even harder. Okay, so thus, the interatomic equilibrium may be reached either inside or outside the time region unit of distance. Okay, so the time region unit of distance is a unit of space divided by the interregional ratio. Another thing that Larson probably could use some more sexy terminology. You got to remember the interatomic distance and the interregional ratio, and the unit time region unit of space, and there's just all this kind of very dry terminology, and you can trip yourself over them. If Larson would maybe come up with if he would have come up with just one word to describe these different phenomena, that might be a step in the right direction too. Instead of just calling it the interregional ratio, just calling it, the Q ratio or something. Okay, the interatomic equilibrium may be reached either inside or outside the time region unit of distance, depending on where the outward rotational forces reach equality with the inward force of the progression of the natural reference system. Extension of the interatomic distance beyond one time region unit does not take the equilibrium system out of the time region, as the boundary of that region is at one full-sized natural unit of distance, not at one time region unit. So far as the interatomic force equilibrium is concerned, therefore, the time region unit of distance does not represent any kind of a critical magnitude. Okay, well, I believe that's where we're going to stop. I would like to, move faster through this, but I don't know that it's really possible to do that with a kind of a freestanding video. Like, you have to kind of cover the background information as well as move forward. And I don't mind re-articulating how the reciprocal system works over and over again, because I believe that even a good student of the reciprocal system kind of needs to hear it repeatedly. It needs to hear it over and over again, the basic fundamental postulates of the reciprocal system and what they mean. But then, that takes a while, and then it takes a while to kind of backtrack about what he's saying and then move forward on what he's going to say. So it's a difficult pedagogical problem, and but I think that it's just better to move slowly through this, because I think that even if you watch every one of my videos, you can get something new out of each one of them. Even if it appears that I'm, re-articulating the same thing, I'm saying them in a slightly different way each time. And so I think you can always get a new nugget of information, a new piece in the puzzle from each episode. And, to a great extent, the understanding of the reciprocal system is like putting together a puzzle, and it is like you have to get one clue at a time, and it's not all going to be there for you. But then when the puzzle starts to fill up, you kind of start to see the bigger picture. Okay, we'll pick up where we left off tomorrow and move forward in our slow way. And thanks for tuning in today. Have